When you study math in college, you at some point encounter transformations, which are that if you have a function f of x, when you apply a transformation, it will give you something else. In particular, today I'll talk about the Fourier transform, more precisely on how the Fourier transform operation is so natural in our world that most often it is just simply waiting to be discovered. To those of us who are unfamiliar about the Fourier transform, this might be a good time for us to stop and ask what a Fourier transform even is. Maybe the best way to introduce the Fourier transform is through sounds and frequencies. So that seems like a good starting point. Consider a tone of some frequency, say C. When you plot the air pressure versus time, you'll get an oscillating pattern, which is a sine curve. Other frequencies like say E, they also look similar. When you play them both, the resulting waveform is a direct sum of the two previous sine curves. After the addition, the curves do look more complicated. The C chord looks like this, and it's made up of three notes, the C, the E, and the G. When you record your voice over a microphone, you get a similar waveform. When you zoom in, you can see it is similar to a sum of sinusoids. This is not really periodic this time, but nevertheless we can still ask the same question. Can this be broken down into sinusoidal curves? Turns out you can, thanks to the Fourier series. The Fourier series is a result that any function can be reconstructed using sums of sines and cosines. The Fourier transform tells you which frequencies are present in this audio sample. It does so by producing a graph of the amplitude versus frequency. The Fourier transform converts a waveform like the audio file you sent and views that very same thing in the frequency domain. Here, we can see all the frequencies that are present in the audio file. Wherever there are peaks, it means the sound of that frequency has a large amplitude. That frequency is one of the dominant frequencies. One way people make use of this fact is in sound editing. Say, a really unwanted high-pitched sound has entered into your recording. You can take a Fourier transform of that recording, which breaks down the recording into constituent frequencies. Then, after identifying the frequency of the unwanted noise, you can simply subtract it and take what's called the inverse Fourier transform, which essentially guesses what waveform must have produced this frequency distribution in the first place. The resulting waveform would be the exact same without that high-pitched noise, essentially because it was removed. The Fourier transform has a lot of applications in sound processing, image processing, electrical engineering, oftentimes in chemistry. There has even been use of Fourier transforms on the seismometer graphs of earthquakes, which at first glance might seem completely unrelated. But my goal with this video is to show you that Fourier transforms are not just a tool that us humans can use. It's not just a math tool with clever application engineering. Like all things in math, the Fourier transform has been in action well before our discovery of it. Let me highlight to you one improperty of the Fourier transform. Notice how when we shift to the frequency domain, we lose all information about the original function. And at the function, we can't tell which frequencies make it up. Also, notice that if your function is really squeezed, it is tough to make it using a sum of sine waves. You will need more waves of different frequencies with decently sized amplitudes. So you should expect the Fourier transform to be more spread out. On the other hand, with a more spread out function, you will require less sine waves to build it, and so the Fourier transform will be more precise with its frequencies. Doesn't this ring any bells? This is the beloved uncertainty principle. It's coming purely from the Fourier transform. The uncertainty principle is more classical than you think. People face this issue while trying to send signals to flying planes. To know the speed, they must pulse for a longer time, which loses info on the location. To know the location, a short pulse loses info on the speed. The uncertainty principle for a quantum particle is that you cannot have precise information on both the position and the momentum. You have to know one at the cost of the other. For a quantum particle, everything is encoded in its wave function. As all waves are sums of sines and cosines, psi is built up upon the basis functions a e to the I kx minus omega t. Taking the Fourier transform must give you amplitudes of these basis functions. A particle with good knowledge in its position is a narrow psi with respect to x. This must necessarily have a Fourier transform that is brought in the spatial frequency. But what does this have to do with momenta? Well, de Broglie equations, momentum equals h bar 2 pi by lambda, 1 by lambda is the spatial frequency. So, the momentum is just a scaled version of this Fourier transform. The broadness remains, and so does the uncertainty principle. Likewise, energy is h bar 2 pi f, where f is the temporal frequency. So, position and momentum form uncertainty pairs, and so does energy and time, all thanks to the Fourier transform. I'll end the discussion with a seemingly unrelated area, but nevertheless quite fascinating. There are Fourier transforms that are happening inside you right now, particularly at your ears. See, this is how your ears look like. Sound enters your ear from here. The auditory canal channels the sound. Basically, it matches the impedance with the eardrum. If not, the eardrum will break. The eardrum vibrates based on the air pressure with time. In other words, f of x is being encoded into the movement of the eardrum. Behind the membrane exist three bones called the ossicles: the malleus, the incus, and the stapes. These act as lever arms that transfer the oscillation. The stapes is connected to the cochlea on the oval window, so the oval window is a membrane that the stapes is attached to, and that will vibrate as the stapes does. The magic happens inside the cochlea. The cochlea is filled with a fluid which transfers the vibrations from the oval window to a membrane that runs through the entire cochlea. When you take the cochlea and unwrap it, the membrane should be laid out horizontally. This membrane is called the basilar membrane. The basilar membrane has variable thickness and mass density here and there, and so each section of the membrane has its own resonant frequency, meaning that the section only vibrates when the vibrating frequency is equal to its resonant frequency. The resonant frequencies increase uniformly. When an incoming wave comes, each section vibrates only when there's an amplitude corresponding to its frequency. Basically, the basilar membrane is a mechanical Fourier analyzer. What exists on the basilar membrane is the Fourier transform of the incoming wave. How cool is that? Your ears are basically a Fourier transform machine in itself. Below the basilar membrane is the organ of Corti, which has many hair cells on it. It's called hair cells as the cells have hair-like projections on them, called the stereocilia. When a particular section of the basilar membrane vibrates, the stereocilia moves underneath and triggers ion channels that then send electrical impulses to your brain. So your brain knows exactly what frequencies are present in the sound that you're hearing. So, the takeaway? Nature has always, like with other math, caught onto Fourier transforms way before us and has been using it in very clever ways. So yeah, it's pretty cool to see how math ends up being used in nature automatically without any human intervention. I find that really fascinating. Anyways, I guess that's it for today. So